So a little bit of kind of where we're at, where we're going. Things I want to mention before we get started. So next week, both classes, Tuesday and Thursday, will likely be replaced with a video. Guarantee, almost 99% guarantee Tuesday's class will, and there's a 95% chance Thursday's class will be as well. So I'll use Canvas to kind of converse with you guys outside of class, but that is the tentative plan moving forward. So you'll have the next topic we're going to talk about is panel data. I'll kind of set things up on Canvas just like I would if we were going to meet in class in person. So I'll kind of put up the next set of slides, data files, do files, anything that I'm using in that video. That problem set is due by the end of next week. So if you have questions, try to get those to me early. I should still hopefully be available a little bit next week via Zoom, right, to kind of meet virtually if you have any questions over that problem set. I'll get the next quiz posted. I think Tuesday I said I was going to post after class. I looked at it again. There's enough questions where I wanted to make sure no one started it before today's class. So I'll post that after class today. I'm going to put the due date on that to be not until the Monday, until after end of the day, Monday after Thanksgiving break. So give you a lot of time to kind of review those practice problems, review the material. Now I would suggest probably trying to do it before then, right? The further you get removed from the material, the more difficult it's going to be. But that quiz will not be related to what those videos are covering next week. It's only everything that we've covered up through this week, right? So, excuse me. That's going to be kind of looking at our interaction terms and then also some of these data issues that we talked about, okay? Other than that, so next week we'll have kind of replacement videos for class. So I'll expect that you're getting on and watching those. I'll expect you know how to deal with panel data issues that I'll discuss through or discuss in those videos. When we come back from Thanksgiving break, because the next week is going to be off because of Thanksgiving break, right? We'll have 2 more weeks before final exam week. So one of those weeks we'll kind of start going through instrumental variables. It'll likely take that full week and maybe spill over into that week before finals. So we might cover a little bit more instrumental variables. If anything else, it'll just be me going through more examples, right? On that on that Tuesday's class. And then the rest of that class, and then on Thursday's class before the final, we'll just be doing review. So I'll get a practice exam up there, likely over Thanksgiving break. You can kind of start looking at and working through. But once we get back from Thanksgiving break, there will still be 1 more assignment and 1 more quiz that's related to panel data, which will be what are in the videos that I'm posting next week. But then also some of the instrumental variable stuff we'll talk about that week right after Thanksgiving, okay? So 1 more assignment, 1 quiz once we get back from Thanksgiving break. And then, of course, the final exam.
Is the final cumulative?
So I said this at the beginning of the semester, but it's like you forgot. The final will just be everything we've covered since the midterm. Now it's cumulative in the sense that like we're still using p-values and but no, it's just going to be over the material that we've covered since the last exam. Yep. Any other questions for me before we kind of jump into material here today? Is that clear? Kind of what the map of the rest of the semester is going to look like? Okay. So, and I've got to my GAs that 4th problem set. You might start seeing kind of grades pop up there. I got them the grading files and everything. So they're going to kind of start taking away at those. So you might see your grade pop up for those problem sets on Canvas here over the next week or so. If there's anything else I want to mention, I think that should cover before we jump into material. Check for questions one more time. Okay. So I understand this stuff is getting a little bit more difficult, right? In fact, it's getting a little bit more conceptual where sometimes we don't have like a nice definitive, I can plug this into here and get a definite answer. We're starting to think a little bit harder about some of the issues that are going to exist in our data sets. Now, the next 2 topics will be a little bit more kind of return to like clear-cut answers to where we'll have some solutions to what we've talked about this week. So last class, we talked about threats to internal, external validity, right? We kind of left off thinking about, well, what if we have measurement error in our independent or our X variable? So we said, as long as it was classical, so as long as we had classical measurement error, this was the idea that the relationship between our measurement error and our independent X variable was not related at all to what the actual level or what the actual value of X was. So this would be like the measurement error was completely random. So when I'm asking people to say report their income, a value they give me, it's going to have some measurement error, but it's completely random. It doesn't depend on if they had higher or lower income values. Now, that we said wasn't really a big issue, because what did that do to our estimate? It's still not no issue. We said if we had classical measurement error, we know the estimate we see for the coefficient will always be closer to 0, or we had a very specific name for that type of bias, which was attenuation bias. Now, we're not as concerned, right? It's relative, but we're not as concerned because we're understating effects there, right? And in fact, it's not that it creates a negative bias, right? It's never going to like flip the sign. It's only going to push it towards 0. So if it's positive, it's just going to be a smaller positive value. If it's negative, smaller negative value. Now, if we had non-classical measurement error, so the example I used was like really intelligent people tend to underreport, whereas less intelligent tend to overreport. So there, the measurement error I see does depend on the actual value for that X variable I'm trying to collect. If we had non-classical measurement error, we said all bets are off. The bias could be that the estimate is higher, could be lower, could even flip the sign, right? We walked through some examples of that last class. So we went through that in Stata. Today, what we're going to talk about is if we have measurement error in our dependent variable. So this is no longer our X variables. We're now thinking about that Y variable. Okay? So, we have the actual Y values, right? So this is just going to be depicted with Y. The values we observe, though, like even if we were still collecting data on income, the actual values we observe, if we're using that as our dependent variable, is going to be what we could now call Y tilde, right? So Y tilde is what we actually see in the data. Okay? Now, we know the actual relationship between X and Y will be between the actual values of X and Y, whatever those two variables are. Now, if I add in some measurement error, what have I done to the equality of this equation? If I add the same thing to both sides, the equations should still hold, right? You add, it's just math, right? If I add something to both sides of an equation, the equality will still hold. So now what do I have on the left-hand side here? I've got the actual Y values plus my measurement error. So when I have the word error here, this is our measurement error. Now it's in the dependent variable, right? It's in the Y values that I see in my data set, Y tilde. Okay. So if we compare this to if we had the actual Y values, well, I still have the usual error that I would have in my regression equations, right? This contains everything that my X variable doesn't explain about Y, right? That was our typical kind of difference between our predicted Y and actual Y. It's just now we're going to have that error plus whatever this measurement error that exists as well, right? So we can kind of think about just like with our independent variables, we can, well, I don't have it rewritten here, but this epsilon plus the measurement error, that's just like a composite error. Essentially, the error that we have in our regression when we're using the observed Y values, it's going to be larger, right? There's just more error that exists. There's more variation that exists in the Y value or the Y variable in our data set. And that's because it now not only includes the true values, but also this measurement error. Excuse me. All right. So will this bias our estimate, right? Well, if the expected value, usually what we need is for the expected value of our error term conditioned on different values for X to always be equal to 0, right? That no matter what the X value is, the errors that our line of best fit is making is 0 across all of them. However, now our error term not only includes our traditional error, but also the measurement error. So the additional condition we now need to hold is that the measurement error for different values of X is still equal to 0. So that was the same thing we said could happen when we had measurement error in the independent variables. We need this condition to hold. What is this really telling us? If the expected value of our measurement error for different values of X is just 0, that's telling us the measurement error is completely random, right? That we have classical measurement error. So now it's not the measurement error that exists in this X variable, it's just now it's the error that exists in our Y variable. If it is equal to 0, then we have an unbiased estimator. Now, I'll kind of given a little bit deeper look into this here in just a second after we look at some actual data. However, because there's more variation, even though we have an unbiased estimator, it can make our standard errors a little bit higher, right? In fact, we'll even like kind of look at the R squared between the actual and the kind of self-reported or the values that have measurement error in them here in a second. But if there's more variation in the Y variable that we now aren't able to explain, it's just this additional random variation. What should happen to my R squared? So let's say I run this very basic regression. I have the actual X and Y values. My R squared is 0.3. My X variable can explain 30% of the variation in my Y variable. Well, if I now have measurement error in my Y variable, and I run that regression where I have the actual X values, but the self-reported or the Y values that have measurement error, well, there's now more variation in that Y variable that's unrelated to the X values. So what should happen to my R squared? It's going to decrease, right? I'm not going to be able to explain it because I can still explain the same amount of variation in Y, but I can't explain any of the variation in the measurement error, right? So we'll kind of see this play out here as we kind of look at some actual data. Now, when will the estimator be biased? Anytime we have the measurement error, and you can kind of think about it here instead of like getting too lost in like the expected value, the measurement error given different values for X is equal to 0. Really, all this is saying is that the measurement error doesn't depend on the values of X. If it does, we're going to have a bias estimator. So let's think about an example where I had Y as self-reported drug use, and X is whether or not the individual, just a dummy variable, 1 if they're a law enforcement officer, 0 if not. So even though everyone is likely to underreport their drug use, what do you think the value that most law enforcement officers are going to report is? If I'm worried about keeping my job and I'm a law enforcement officer and you ask me about my drug use, I'm probably going to tell you 0, right? If I'm worried about this information getting out of tied to me at all, so we would expect the value of X, whether or not they were a law enforcement officer, to actually predict the measurement error is even larger, right? So anytime that measurement error is related to your X variable, you've got non-classical measurement error, and that will cause bias in your estimate. So it's the same sort of story we talked about for the measurement error in your independent variable. It's just now, if it's not related to the X value, now you don't have attenuation bias, you don't have any bias at all. So that's better for us, right? We know we're getting an accurate kind of identification of the relationship between X and Y here. Okay, so let's take a look at this in Stata, and I will then also have something else I'll kind of write out what I think will help. So we're going to scroll down here to where we're talking about measurement error in the dependent variable. I'm going to open up that life expectancy data once again. I got lazy. This was if I did it from my computer, so I'm just going to have to make sure I put the correct file path in there. Whoops. Okay. So I've got this data open. I'm going to rescale the GDP variable we said just to make the coefficient easier to look at. I'm going to set the seed so we're all dealing with the same random numbers. I'm then going to create some random measurement error, which is between -10 and $10,000. So just some random value for every observation. I'm going to choose a random number somewhere in this range. I'm then going to create my new GDP variable, which is my dependent variable, which includes the actual GDP plus this random measurement error. Okay. Excuse me. So I'm going to go ahead and run that. Excuse me. So I've now gotten my data set. The GDP that includes the measurement error. Okay. So let's take a look at what happens, right? If I just run this relationship between GDP and BMI, right? And this is with the actual values, right? So this is kind of like a hypothetical. We're not usually in practice, we're not going to generate measurement error. I'm just doing it to show you what happens if you do have the measurement error. Right? So if I run the regression with the actual values, it's the same thing we had last class. We get that coefficient estimate of what, about 60,088. So we notice our R squared there is 0.0091. If I run this regression, but instead I've got random measurement error in my dependent variable. Now, what I was telling you is that if this was completely random, it's not related to the X values of BMI at all, what should this do to my estimate? Cause it's completely random, it's classical. We said our coefficient would be unbiased, which means we should see the value of 60,088. or we're doing this from one set of random numbers, so it should be close, right? In fact, I'll show you how we can prove that it's going to be exactly 60,088 if we were to take like an infinite number of samples. So pretty close, right? 60,096, not very far off, right? Now, once again, this is from one sample. Excuse me. So we would need to take a ton of samples to really prove that it's exactly the same value. Now, I can't really tell out to the fourth decimal, and this is where the concept of knowing what's happening will matter. Even though it looks like my R squared values are the same here, right? You could actually, well, I'll just mention it. We can't see it out to the fourth decimal, but if we could, we know that that regression that had the measurement error in it should have a slightly smaller R squared. So I think we'll kind of see this play out with some later regressions. Here, out to the fourth decimal, it doesn't look like it changed anything, but it will, to some level, to some decimal, it should decrease that R squared. Okay. The real thing I want to focus on here is our estimate with this classical random measurement error in the dependent variable, no bias. Okay. Now, we want to prove this to ourselves a little bit more. And I think before I say this, let me make sure. Yeah, I put up these what we call Monte Carlo simulations. So this was the idea when I'm running, instead of doing one set of random numbers, I'm doing 100 and running this regression. So that should give me a little bit more accurate idea. So let's go here. I'm going to clear out these programs. Actually, what I need to do is change my file path. Oops. So that I'm using the data that's on this iDrive, not my personal computer. So here I'm going to define this program that opens that life expectancy data, scales GDP, creates the random measurement error. Now here I created it slightly differently, and this is just more of to prove the point that it doesn't matter what distribution we're pulling it from. It's just random. Doesn't matter if it's random from a uniform, random from a normal distribution, right? I'm still going to end up with unbiased estimates. So I'm going to define this program and then run it 100 different times, save the coefficient estimates, and then look at the mean of that coefficient estimate. So I'm going to go ahead. Oh, actually, I'm on the wrong one because that was from last class. We're doing dependent variable. Here we are. Same idea, right? But now I'm going to be saving those coefficients when the dependent variable has the measurement error in it, right? So we did the other ones last class. So we don't have to clear programs because we haven't defined any yet, but in practice, you should always kind of include that just in case, we're running this do file all at once. We've done it across 2 classes, so we didn't have to worry about that. So I'm going to go ahead and run this. What did I forget to do? Change my file path to be working off of my OneDrive. Whoops. Okay. So go ahead and run this. Oh, what didn't I like there? Put the word used twice. I copied it. There we go. All right. Now notice when I look at the mean of those 100 different random, so it's 100, so it's random numbers, but 100 different sets of random numbers, the coefficient estimate I get is exactly that 60,088 that we found if we were using the actual data. Right? So with only one sample, it looks like it's pretty close, right? Looks like it's unbiased. But if we were to take 100 samples, we can see, oh yeah, on average, it'll be completely unbiased. It's the exact same value. Okay. Any questions on this before we keep moving? Is it just to be clear, I'm not going to make you run these Monte Carlo simulations. I'm kind of showing you what you can do in Stata, and it's really just a data support for the theory that we're talking about, right? We can see that if we were able to take not just one random sample, but 100, on average, we get the exact same coefficient as if we didn't have measurement error at all. Okay. So I'm going to scroll down here. We'll go back to the old data file, and I'm going to make sure I didn't put use in there twice. So I'm going to do the same thing I had before, but now I'm going to create this second measurement error, which is the first one. It's just the randomness. But now the measurement error, and this is the most egregious way of doing this, it now depends on, I'm multiplying it by the actual GDP level. Well, don't actually want that here. What I actually want is the values of the X variable. So I've made the measurement error now be a direct function of my X variable. So now when I think about is the expected value of my error, my measurement error, is it going to be different for different values of BMI? Well, for sure, it's a function of BMI. So this is like the most egregious way of building in that measurement error. That is what we would now call non-classical, right? Our measurement error now depends on these different values for X, okay? So we'll go ahead, create that variable. I'm now going to run a regression where I use this self-reported, this GDP that has measurement error that is non-classical. If I run this regression now with my non-classical measurement error, not only do I not see 60,088, I see something way lower, right? And in fact, talking about like our R squared goes to like 0. So even with classical measurement error, we said, you know, that R squared would be a little bit lower. We have non-classical, we don't know what's going to happen to our coefficient. In fact, I could probably generate some type of a relationship. Let me think here. I'll prove this to you. I get it to be like 0.15. I think I can make it larger here. What do I want to do here? I could do plus 30 times BMI. So I can just kind of all these different relationships with a measurement error depends. And notice the coefficient is jumping all over the place, right? But as long as that measurement error is dependent on the values of your X variable BMI, you're not going to end up with an unbiased estimator, right? Now, if it was classical, we said, going back up here, well, now we're getting something that's exactly, it's unbiased, right? It's exactly what that relationship between the X. So it's kind of nice because if we're concerned about measurement error, but it's in our dependent variable, as long as we think it's completely random, doesn't mess up our results, right? Any questions over anything? I want to see something there again. Okay. So I want to give a little bit more insight behind this, and this isn't quite technically correct, but it's a better way to, I think it's an easier way for you guys to think about it. So let's say I had my GDP variable. There we go. I have a marker that works. And this is kind of my self-reported GDP. And we had what? BMI over here. And I said, there's this error term, but there's also, and I'm just going to shorthand this with my measurement error, right? Now, I can't see what that measurement error is. I don't know what it is for every observation. I just know that it exists. So when I run this regression, what is the estimate I'm going to see on BMI? Well, it's going to be the actual effect of BMI on GDPs. But we can think about, it's almost like I'm not including that measurement. It's not in my regression. It's not a separate variable. What if I would include it? It's essentially because I'm not actually, you know, when I run this regression, it's still just one X variable. It's basically like I have an omitted variable, right? So what would the bias be caused if we had an omitted variable? We said that would be the coefficient on my measurement error if I did include it. Now we're not, right? As a whole, we don't have data on that. So it would have been the effect that the measurement error would have had multiplied by the covariance between the X variable and the variable I omitted. Okay. So I know that when I have measurement error, it's almost like I said, an easier way to think about it, it's an omitted variable. It's something I don't know the value of, right? But I do know that how far off I am. Well, that's going to impact my Y value because the actual Y value is not what I see in my data. It's that value plus or minus this measurement error. So I know that it's going to influence y. I know that it should be included in my regression. So when will my estimate, I said, this doesn't make sense, right? I said that this is going to be an unbiased estimate, but I'm now telling you we have this additional, what looks like an omitted variable bias. Well, what if I have classical measurement error such that that measurement error for different values of BMI, the expected value is always 0? What would be 0 up here? Oh, sorry, that would help. So if I have the expected value of my measurement error for different values of BMI 0, what would the covariance of BMI measurement error be? If it's completely random, doesn't depend on BMI, my covariance here would be 0. So if I have classical measurement error, this covariance is 0, the bias goes away, and I've got an unbiased estimator. Anytime it depends on the levels of my X variable, well, this is now, I shouldn't even say it's just not 0. Could be positive, could be negative. Well, now my estimate will have a bias in it, right? So with classical measurement error, it's almost like we don't have to worry about the omitted variable bias from the measurement error. If it's non-classical, that covariance will not be 0, and our estimates will now include this additional number or this additional bias. Okay. Any questions on that? Is that hopefully, I'm trying to use something we've already talked about to make a little more sense of this. Okay. Now, I will not ask you, and this would be an unfair question, to ask you to sign or size this bias. That would be very difficult because now I'd have to have actual data on the measurement error, be able to figure out the covariance. Not only that, I need to know, even if I don't have data, even to just put a sign to this bias, well, I don't know what function the measurement, I don't know what distribution the measurement error is coming from. I have no idea what the impact of that measurement error would be if I included it in my regression. So it would never be something we can really do in practice to sign or size that measurement error. And I say that based off of what we're going to talk about. If you were to kind of continue to go into higher level statistics, well, we know certain things about certain distributions, so we might know how it is correlated with the y, and we could put a sign to it. But for the sake of what we're doing, we just need to know when it is classical, this covariance would be 0, our bias is eliminated. When it's non-classical, there's going to be some bias, and we don't know what it is. That's the end story for us. Okay. Any questions on that? Okay. Sure, there's no questions. Yeah.
When you ask us about this, then all we have to say is if there will be bias or if there won't be based on the classical or non-classical.
Yep. So we think about and think about why. That would be a type of question I could ask you, and think about supporting why you think it's classical or non-classical. Classical measurement error means that you think the relation. It helps to just think about it as the covariance instead of this expected value given to. If your X variables are or the X variable you're looking at is correlated at all with that measurement error, right? So if I did have something here, like instead of BMIs, let's say I was trying to predict the number of days you missed class based off of your alcohol consumption. Well, there, if I think, the number of days, well, that's not a good one because I want dependent variable. Let's say I'm trying to predict your, let's say I'm trying to predict self-reported income, and then kind of alcohol consumption is my X variable. If for whatever reason, I think that, drunks might not be able to remember what their exact income is more than people who are sober. Well, there, my measurement error independent variable is going to depend on their alcohol consumption, right? And so there, I think I have non-classical measurement error. I think I might have a bias that exists there. But being kind of explain why it is non-classical, and that's because whatever this measurement error is in my dependent variable, it is going to be impacted by what level that X variable is, or what the value of that X variable is. Right? What would be another kind of thing I could think about? So let's say I had let's say I was trying to predict So my dependent variable is whether or not someone, we haven't talked about dummies, but same logic applies. Let's say I want to predict my Y variable is I ask people whether or not they were going to vote for Donald Trump before the election, right? So I know that people aren't going to necessarily always tell me who they're going to vote for. I know I'm going to have measurement error, right? So as long as that measurement error isn't related to the X variable. So let's say I'm trying to predict whether or not they're going to vote for Trump based off of, I don't know, their age, right? Well, we know that older voters tend to lean a little bit more right, and so maybe I could, think there's a relationship there. Well, the measurement error, whether or not they lie to me or whether or not they don't tell me who they're going to vote for, likely doesn't depend on their age. It's not probably going to be correlated. So it's probably classical measurement error. So there, I could probably get a pretty good idea about the relationship between age and whether or not someone's going to vote for Trump. Now, let's say instead of age, I'm using, I don't know, the percent of the county they live in that's Democratic or that voted Democrat in the last election. Well, I know that would make it less likely they vote for Trump, but I know that people who live in predominantly Democratic areas, what's going to be true about their measurement error? They're probably going to be a lot more likely to tell me that they aren't going to vote for Trump, even though they actually are. As opposed to lower levels, they're less likely to lie to me, or the measurement error is going to be smaller. So there I would have an example where I know that that measurement error, how much is going to be under or over reported, depended on that independent variable, that X variable. So knowing kind of what classical and non-classical error means and kind of be able to describe that between two variables, that might be something that would be fair game as well. Does that make sense? Also, I came up with that off the top of my head, so you could maybe poke holes in those examples, but I think that they're good off the top of my head. Yeah.
So basically, I can think of the reason why, like a variable would be affected by another variable. It's a non-classical bias, right? Like if there's a relationship between the two.
It's not quite the other variable being impacted, right? It wasn't whether or not they're going to vote for Trump that was impacted by the measurement error. It was whether or not they report to me, right? Whether or not that you think about it this way. It's whether or not the under or over reporting of someone would be related to that X variable.
Okay, so if the error is related to the variable, right?
Yes.
Okay.
It is likely the actual Y value will be related, but that's not what that's not what's going to cause our bias. What's causing the bias is if that measurement error, not the actual Y value, but the measurement error included in it, is somehow related to those values of X.
Okay.
Is that?
Yeah, that makes sense.
Like I said, this gets to be a little more conceptual. It's harder to
So,
think about.
Like that, the example of if you're smarter, you'll underreport, that would be non-classical, right?
Yeah, so let's say I wanted to predict. Let me think of one. Oh, I know. So you want to do, let's say I want to predict wages based off of IQ. And for whatever reason, wages, I'm not collecting from IRS data, I'm self-reported. So I've got the actual IQs of individuals, maybe I'd give them an IQ test, but I had to ask them what their income was. So the measurement error exists in my dependent variable. Well, will that measurement error, so this is just the fact that people are going to over or under report. It isn't that they're over or under reporting their own IQ now. That was the independent variable measurement error. Now it would have to be that the measurement error reported in their wages depends on their IQ. So I could think of a story that goes either way there. One story could be none of us know exactly the number we make. So regardless of our IQ, we're always going to be a little bit off. You could probably argue though, individuals with higher IQs, right? Are they going to be more likely to know what their exact wages are? Well, maybe, right? There's a story there, the higher IQs, they might be more likely to be on top of their finances and know a closer number. And so their under or over reporting could depend on their IQ, right? But it's now the measurement error in your Y variable. It's not that it depends on the values of wages. It's still that it depends on whatever the values of that X variable are. It's just now the measurement error isn't in the X variable, it's in the Y variable. Does that help a little bit? Yeah, but we could think of, all these different kind of examples. Yeah,
So as long as we like define why we think it's classical or non-classical, like you'll grade it.
yeah, if I left it open-ended, then I would just be looking for, are you giving me a correct explanation? Based off your assumptions, are you telling me why you think those two things are correlated or not? And as long as you give me a justification that matches up with what you're telling me, then yeah, it would be counted as correct. Yeah. And what I might be more likely to do is tell you, oh, the covariant part of the problem might be, we know that people with higher IQs tend to remember their wages more, right? Or tell you something about what that covariance would be. Yep. Any other questions on that? Okay. All right, so this is good. We're getting this kind of locked down here, so we'll go till 45. So I want to make sure I save us enough time to go through the rest of this. So I'll go through this a little quicker. It's kind of a fun little setup to some things we're going to talk about with missing data. But also this topic is, there's not as many clear-cut answers, and we have to think a little bit harder about how this could impact our results, right? So no one took 370 with me here, did they, this past summer? Probably not. Okay, so you won't have to see this example again. I use this to set some stuff up there too. So in 1936, there was a presidential election, and my grandparents had this thing. I don't know, you guys might be young enough now, you've ever seen this, but there's like these little magazines called the Literary Digest, right? So they were like monthly subscriptions. They were usually like topical, things that were going on in the country at the time. So this company got this wise idea. We're going to send out 10 million surveys, try to predict the upcoming election results, and put it in our magazine, right? Trying to give us some credibility. Well, they sent out 10 million. So with a sample size, if they could get everybody to respond to this, a sample size of 10 million is really high. So what would be true about our prediction? It's going to be pretty close to the population value, the actual outcome of the election. So they sent this out. If you've ever done anything with surveys, I don't know, clubs or different, they got 2.5 million back. Getting a 25% response rate is really good with surveys. Every survey I get from my phone, I delete, right? So getting 25% is really good. They saw this like, we got a sample size of 2.5 million. We're almost guaranteed to be able to make the right prediction. So they looked at these responses about who people were going to vote for in the upcoming election, and they predicted a landslide, right? 57% of the popular vote, 370 of the electoral vote, but they predicted it for Landon. I mean, I think I'd remember if somebody named Alf was elected president, right? And so they predicted the outcome exactly the opposite direction. It was in fact I must have deleted one slide. It's a landslide for FDR. We know he won. If you go back, he won by a large margin. So how did they get it so wrong, right? So there is a really good example to use two types of bias, right? So the first is going to be what we call selection bias, right? So selection bias is if my sample is over or underrepresenting a specific group, right? So what's a good example of a selection bias? I can think of like, maybe I'm interested in the alcohol habits of individuals and how that impacts their overall health, right? Well, if I go out and grab data, I'm like, oh, I could gather data on this. I'm going to ask people how many times they, I don't know, get sick over the past year and what their alcohol consumption is. And I've got a nice kind of built-in base of all my students. I'll just put out some surveys on Canvas. What's going to be true about my data set? It is vastly overrepresenting college-age students. I know that their drinking habits do not look the same as the national population, right? So I know I have a built-in selection bias, right? So anytime I'm over or under selecting a group in my sample, my results aren't going to be valid. They're going to be biased. They won't be unbiased because I'm looking only at a specific subgroup. Now, am I understanding something about the relationship between drinking habits and health for college students? Yes. But this selection bias is kind of a threat to our external validity, right? It's not going to tell us the effect for everyone in that population. We could also have a non-response bias. So this could just be, maybe we send out these mailers I sent 5 million to registered Republicans, 5 million to registered Democrats. For whatever reason, none of the Democrats responded, 2.5 million Republicans did. Well, now I know my sample, I'm gonna see that the Republican candidate is likely gonna win, right? Even if they're not a very popular candidate within their own party, right? It's gonna look like they're gonna win. So I have these two types of bias, and we'll kind of think about some other examples here in a second after I go through this. But both of them would cause basically bias, right? Selection bias, non-response bias. So this, we want to have a sample that reflects the population in terms of like across all attributes. So this is a really good example to highlight both the non-response and selection bias, because there was a group of researchers that went out and where they were able to figure out who was in this original 10 million people. They reached out to a lot of them, as I forget what year it was well down the road, but to collect more data on them and see like who did they actually vote for, right? And did they respond to this survey originally? So what the Literary Digest did before these researchers got their hands on these names, where did these 10 million names come from? Did they select 10 million random people? That would have been great, but they didn't, right? So the process they used to get these 10 million names is they cross-reference names on car registrations and telephone books, because they wanted to make sure like these people are living in America, they're more likely to be, citizens who are going to be voting. So these are actual people that exist that have a car under their name and a telephone line. Who owned cars in 1936? Did everybody have cars? Who had cars? People who had a lot of money, right? Not only that, who had their own telephone line? Well, might be related to income, but my grandparents, my dad, when he was growing up, tells me stories of like, they didn't have their own phone line. They had these like I forget what they call, not community phone lines, there's a specific word, right? Everyone in kind of the same country mile was on the exact same shared phone line. So I'm not going to be getting people who are kind of in rural areas, right? So I have this selection that I was using to get these names. It's going to cause selection bias into my sample, right? So we would like to, when we're getting samples, make sure it's completely random. If we use some process, we need to be careful and think about how could that process, even though it seems inconspicuous, right? I'm just trying to go out and make sure I'm getting names of actual citizens. It could be building in some selection bias. So when these researchers went back out and they contacted a lot of these people who voted in the actual 1936 election and responded to these surveys, what they found was when they reached back out to them, the people who owned a car and a telephone, 53% of them actually did vote for Landon. So that prediction of 57, a little bit high there, but it would have been at least on the right side, right? They would have had the right candidate winning. Now, these would be people who own a car and a telephone. These are likely going to be people who are like wealthier and live in inner cities, right? What about if they would have just used the same process, but not required you to be in both? If you only owned a car, right? So this might be that you're wealthier, right? But you're more likely to kind of be out away from the city. 60% of those people voted for Roosevelt. People who only owned a telephone, 62%. And if they had neither, 72. So if they would have simply gathered these names based off of, do you have a car or a telephone, they would have got a lot more accurate results, right? But because they required the names to be in both of these categories, they ended up with a selection bias. Is that kind of clear what I'm getting? Any questions on it? Shouldn't be anything too crazy. Now, what they also did, I kind of already mentioned, what would a non-response bias be? Like if only Republicans sent these mailers back. So this was like, I forget, I should have revisited this paper because I don't even think I forget their argument, but I remember not believing it. And I remember just being like, I wonder where this comes from. But notice, it doesn't matter what group, even if they would have taken names that weren't in telephone books and didn't have a car, just people that were alive in the 1936 election and voted. So what they did was they took these group of names from people who voted in the 1936 election. They sent them another survey, like I guess I think this was in like the 70s or 80s. And the researchers found that this additional survey, every single group, right, whether or not you only had a car, only telephone, both or neither, the people that reported as voting for Landon were more likely to return a second survey. Why that's the case? If I remember right, like the explanation was something about voting for the Republican candidate, civic like pride and things are a little bit higher, and so maybe they felt like they need to respond to a political survey a little bit more. I don't know if I buy that as much, but here this is a good example of it doesn't matter how we selected these names. Even if we selected people from every category, we would have had a non-response bias built in. People who voted for FDR were just a little bit less likely to kind of respond. Okay. Any questions on that before we keep moving here? It's kind of a basic example to set up this idea. So what's something that's a little bit more realistic? Like when we go out and gather data, we can kind of shut down that selection bias. But what's something that we can't shut down that will cause a selection bias is if we have missing data, right? So every data set I've given you up to this point, I've tried to take out all the missing observations, right? So we haven't really dealt with any missing data. So I'll show you what that looks like in Stata here in a second. But if I have completely random missing data, well, I can think about this as if I had like a random sample of 2,000 people. And for whatever reason, the two variables I want to run a regression with, 100 of the people in that sample don't have data, right? They're missing a value. So if I wanted to predict, I don't know, maybe I wanted to predict something like savings, right? Based off of, I don't know, individual age. I don't know, whatever, that might be the two variables I want to look at. If for whatever reason I have people in my data set where I have their savings, but for some reason, there was a data entry error, they just didn't fill out when they were, maybe I grabbed this like savings from like bank account data for whatever reason, they just didn't have the individual's age. Well, if I'm missing 100 random observations, it's basically just like I went from a sample size of 2,000 to 1,900. But if it's random who is missing, it's still like I just have a smaller random data set. So if we have random missing data, what's that going to do to our estimate? It's going to be unbiased. Right? So you basically just have a smaller random sample. Now, even though the estimate is unbiased, because I have a smaller sample relative to if I had no missing data, what's going to be true about my standard errors? They're going to be a little bit larger, and my statistical significance, it's going to be a little bit, depends how you want to say, like small, like the p-value will be larger, it's less likely we find statistical significance. Right? So that's if it's completely random, right? And we'll go through some state examples here in a sec where I can kind of prove or I'll show this to you. So the end story is if it's random missing data, just like I have a smaller sample size. Okay? Now, what if the missing values are not random, but they're correlated with the X variable, right? So let's say I was doing that savings and age one. Who might I be more likely to be missing the age on? Maybe someone doesn't want to report what their age is. Do you think people who are older or younger care about that? Do you care about telling someone that you're 20 or 21? Do you think someone who's, I don't know, in their 50s might care, right? For whatever reason, some people do, right? And so there I might just have people not responding. I might have missing values for age, not for lower values of age, but only for higher values. Well, now it's not completely random. I don't just have a smaller sample. I have a smaller sample that is going to tend to be lower ages on average than the entire population. So anytime this missing data is correlated with our X variable, we're going to actually end up with some type of bias, right? Or sorry, not my X variable, I went ahead, right? Here we go. With my Y variable, right? I was trying to kind of use age there. So if we've got missing observations correlated with Y, right there, the expected value of our error term for different values of X is not going to be equal to 0. Now we're going to have kind of this unbiased estimate. It's essentially like what we had with that non-response bias, right? So I'll kind of work through some actual data examples here. The other one that I skipped through here real quick, excuse me, would be, let's say I've got missing observations that are correlated with my X variable. We actually can end up with unbiased estimates here. It's just that we might have, we'd say they're unbiased in the sense for the population that I have, they'll be accurate. But whatever group is left out, I might not be able to take my estimates and extend them to that group that was missing. I'll give you a visual on this, right? Maybe, there we go. So let's say instead I had missing values. And I'm trying to look at something like, so I want to do age. And what did I have here? I had correlated with X. So let's say I've got, oh, what's a good one? We could really do anything we want. We'll do like the amount they have invested in the savings. So let's assume just for a second that as you get older, you tend to invest more and more into savings the older you get. And it's probably not a linear relationship, but we'll, for the sake of this example, assume that it is. All right. So if I, for some reason, have missing data, and in my example, it tends to be for older individuals. So let's say, I don't know, I don't see anyone in my data. Everyone over 55 just won't tell me their age. This is like the most extreme example of it, right? But I would still estimate the data that I would have would only be here. So I'm still estimating that same line of best fit. Notice I'm still going to end up with the same coefficient, right? That slope is still exactly the same. It's just that I've estimated it only using kind of part of that data. Now, why might that be a threat to external validity? Well, for individuals under 55, I know that my estimate is going to be unbiased, right? But what if the effect wasn't linear, right? Well, if the effect wasn't linear, there I'm thinking about, let's say I have the exact same thing, where I've got age now, savings. Let's say now it looks something like this. And I don't know, you hit a certain age and you start saving a lot more, right? Well, now if I'm just simply estimating this as a linear relationship, if I were to exclude everybody over 55, what is my line of best fit going to look like? Something like this, right? With the slope being beta. If I were to use all observations, I had no missing data. Well, if it's nonlinear, but I try to make it linear, I'm going to end up with a much different slope. So if I have some nonlinearities that exist in the data, well, then it does matter that my missing data was dependent on the actual values for X. But if we have a linear effect, it doesn't matter, right? Because even if I'm missing all of these older ages, I'm still going to end up with the same estimator. So that slide, I should probably add to it because it's not technically correct, given that we're talking about these data issues after we've talked about nonlinearities. If we have linear relationships, then yes, missing data that depends on the X value doesn't matter. But if we have nonlinearities, there, missing data could cause us to come up with very different estimated effects if the relationship is nonlinear. And I probably won't kind of push you that far here. I just wanted to be complete, kind of mention that here. Okay. All right. So, any questions before we move? I've got some stuff I want to show you in Stata. Kind of end, but I think a little bit early here because it shouldn't take us too long to get through it. And I might save this for the video that I record. So just give it, we'll see how much time we have. So down here in that data issues file, I'm going to use this birth weight data we've used a decent amount this semester that's just kind of free and it's kind of existing behind the scenes in Stata. So I'm going to use that birth weight file. I'm then going to generate just some random numbers for every single observation, sort them, and then I'm going to create this variable that's a 1 for the first 1,000 observations, 0 for the remaining. So I'll show you what this really did. And I wouldn't make you do this. It's more to kind of prove to yourself that random data doesn't matter. So I created this random variable. I then sorted it from smallest to largest, right? It's just between 0 and 1. For the first 1,000 observations, I'm going to say those are the individuals. If I can get there, where is that? There we go. That I'm going to assume didn't have missing data. For everybody where there's a 0, I'm going to assume for whatever reason, I was missing their information. Right? So in my do file, I'm gonna generate this new variable, which is family income. So I think I eventually predict birth weight, and it depends on family income. Well, I'm gonna assume that the variable I had for family income was just randomly missing for some people, okay? So I'm gonna create this new family income variable that just has a random number of people missing. I think the data set we had here was like 1,388. We're only looking at 1,000 non-missing, so like 388 random missing values. So I'm gonna create that variable. I'm then gonna run my regression to kind of have my like starting point, where if I had no missing data at all from this data set. So I'm gonna go ahead and run that regression, and I see, okay, I think family income here was in thousands. I just like 65,000, and this is some older data, that's why you see some lower values in here. But for every $1,000 increase in family income, the predicted birth weight would change by 0.007. That was kind of what the estimate should be. Now, if I have random missing data, and I were to run this same regression, but I run it for the family income variable where I'm missing, for whatever reason, 388 of the observations. Well, if it's completely random, that's how I was choosing these observations, it should cause no bias in my estimate. So if I run this, well, sure enough, it looks like it's a little bit off, but it's really close. Excuse me. Now, what I would need to do to prove to you that you actually will see the same estimate is not just base this off of one set of random numbers, but the average of 100 sets or 1,000 sets of random numbers. So that's what I'm going to do here. I'm going to randomly generate some numbers, select a different 1,000 random observations every single time where 388 will be missing. Run that regression that I was running before, save all the coefficient estimates, and then summarize to find what would the average of those 100 different random numbers would be. So this is my Monte Carlo simulation. If I do this, this one takes a little bit longer, right? But I should see that the average across those 100 different random kind of numbers, random missing values, should be, I get 0.0074, or at least something pretty close to it, right? Now, to get even closer, I should do this like 1,000 times, should do it 10,000 times, and that mean is just gonna get closer and closer to that true coefficient. So missing values, as long as they're random, doesn't matter. Now, this is kind of an egregious way of looking at missing values, but let's say I do the same thing, but I'm only gonna run this regression if the family income is below 25 or below 25,000. Well, it's kind of like with my age example earlier. I literally just kicked out all, so it's like the most extreme way of having missing data that is correlated with my independent variable. So if I do that, not only do I not get 0.007, the estimate is 0.01. It's quite a bit, right? I have a huge bias in my estimate. Same kind of idea. I could do the same thing, but miss, and I put draw here for what I already drew for you guys in terms of age. But I can do the same thing, but for different values of y. Notice there, I'm also getting kind of this bias estimate, right? So it doesn't matter if the missing data is correlated with my x or my y variable, it still can cause a bias in this coefficient, right? So ultimately, what do we want? We want random missing data, or we want random measurement error, right? Those are the scenarios where we know that we either have no bias, or we said if we have random measurement error in the independent, it's not that we don't have any bias, but we at least know it's attenuation bias. Okay. All right. Any questions over any, that shouldn't be too crazy, yeah.
Before you said it one more time. The type of bias we want.
So ideally what we want is no bias. And when is no bias created? When we have either random missing data, so it's not correlated with X or Y, or we have random measurement error, right? That it's not correlated with those X values. Those are the ideal scenarios, right? I mean, they're not ideal, and we would like no measurement error or no missing data, but those are the ones where we're not going to be concerned with bias in our estimates. And I should be a little more precise. The measurement error, even if it's classical, if it is random, but it's in our independent variable, we said it's not that there's no bias. We said there it's that we have attenuation bias, but that's the best we could do with measurement error in the independent variable. All right. Any other questions over anything there? So we will have time. I'll introduce this topic. It's nothing crazy. I'm also not going to ask you questions on it in terms of the material that we've covered today. Oh, there we go. Because the solutions to it, we'll kind of revisit it once we get to that topic of instrumental variables. So I just want to bring up, and it's kind of like it's kind of like measurement error, but not quite. Let's say I have two variables. And y is going to be some function of x. So y depends on this x variable. But x will also be a function of, or it depends on what the level of y is. So you can kind of think about what a good example of this would be. So let's say I'm thinking about, the number of firms entering a market, right? I know that as more firms, if I'm trying to predict how many firms are going to enter a market, then I'm trying to do that based off of price. Well, as the price goes up, what's going to happen to the number of firms that enter that market? So if price goes up, it's more likely profits are positive, firms enter. The only problem is as firms enter that market, what impact is that going to have on the price? It's going to push it down. So there's a lot of examples in economics going back to like introductory micro or intro micro, where we know that we're going to have what we call simultaneity issues or simultaneous causality, right? That yes, the number of firms that enter a market is dependent on the price, but the price is also dependent on the number of firms that enter a market. And then the number of firms that enter a market is dependent, right? So it's going to be this kind of cyclical relationship between these two variables. So anytime we have that, you could kind of just rewrite this. Plug in that function you have for x. Well, now you're like trying to predict y as a function of y. You can't do that, right? We know that we're going to have unbiased estimates unbiased. We're going to have biased estimates if we do that. So if we ever have two variables that we think are both functions of each other, we've kind of gotten away from this a little bit of like really focusing on the basics. When we talk about dependent and independent variables, we're literally saying that y is dependent on x. We're really the underlying assumption there is that x doesn't depend on y at all, right? It's that when x changes, it's causing y to change, but not the reverse. If that's ever not the case, like in the example I gave you with the number of firms and the price, our regression results are going to be completely biased. They're not going to be reliable at all. Now we have some solutions to this, which we'll talk about kind of towards the end of class, not class, but the end of the semester, the end of the course, which is instrumental variables, which is like we might want to estimate. So I said price and number of firms, but you can think about like this is like price and quantity in the market. We might want to measure elasticities. Well, we really can't do that because the price is dependent on quantity and quantity sold is dependent on price. But we have some tools using instrumental variables where we can actually still estimate what those demand curves actually look like, right? Based off price and quantity data. So we'll talk about those solutions kind of later on. With that being said, I'm going to end this here.